In applied research, there is a specific moment when thousands of iterations finish, the error rate drops, and an algorithm locks into a stable point estimate. To understand why this stability can be misleading, we look at the forward map. This illustrates the baseline requirement for identifying a parameter. You have a complex, hidden structural state at the top, and the data we can actually measure at the bottom. For the data to identify the true state, this mapping must be injective. It must be strictly one-to-one, but often that requirement fails. Here, multiple distinct structural states all funnel into the exact same point in the observation space. This grouping is an observational equivalence class. If reality exists anywhere inside that perimeter, the data we collect will look identical. Repeated sampling from this regime will never distinguish one point from another. Across diverse fields, this leads to a persistent misinterpretation, the assumption that because a software output is unique, the data itself identified that answer. A unique computational output is not, by itself, an identified structural answer. We must account for why the algorithm returns a single answer when the data cannot mathematically distinguish between these states. The algorithm returns one answer because the model contains a mathematical rule that chooses a single point from the observationally compatible set. This rule takes many forms: a Bayesian prior, a calibration target, a penalty function, an equality constraint, or even just an algorithmic tiebreaker. The research synthesizes these different mathematical tools under one term, the selector. The risk is that in published research, the narrowing power of the artificial selector is frequently attributed to the empirical data. This allows assumptions to be presented as data-driven discoveries. We can visualize this inside a 3D parameter space. Here, a perfectly fluid surface represents a landscape of equal likelihood. Because the surface is flat, the algorithm has no gradient to follow. No single point is mathematically better than its neighbors. This topographical plot shows an exact invariance, or an equivalence ridge. Within this valley, the observations provide zero distinguishing power. Now we introduce a selector. It acts as a rigid external constraint, cutting across the data's flat landscape. At the point of intersection, a global minimum is created. But this point is artificial. It exists because the plane intersects the valley, not because the data-driven valley has a true bottom. The algorithm descends to this new point and successfully converges, reporting a unique output. This geometry enables a specific type of evidential overreach. It allows researchers to treat the precision of the intersection as if it were identification provided by the data. While the math to compute the point is correct, the resulting scientific claim is often an illusion engineered by the intersecting plane rather than the shape of the observations. To see how this manifests in applied research, we look at epidemic severity models, where the data only tracks confirmed cases. The observed cases are a product of two unknown variables, the true severity and the detection rate. This creates an exact product scaling invariance. Doubling the severity while having the detection rate yields the same number of observed cases. The data alone cannot distinguish between a mild virus with high detection and a severe virus with low detection. In this field, priors on initial conditions or delay distributions often act as the selector, locking in the detection rate to force a unique estimate for severity. We see a similar geometric pattern in climate science regarding aerosol forcing and climate sensitivity. Climate models often lack exact symmetry, but possess practical regions, zones that are essentially flat given our current observation limits. Here, parameter priors or model weights act as the tiebreakers along those ridges. An audit of these fields reveals a shared pattern. Studies frequently report these unique point estimates as if they were data identified, while the underlying equivalence causes and the selectors that narrowed them are omitted from the final interpretation. To audit any model's output, the paper proposes 4 diagnostic tests to separate observations from assumptions. Test 1 is the invariance test. Can the headline scientific quantity change while the observable fit remains identical? Test 2 is the provenance test. You must trace every narrowing rule. Was it derived from empirical evidence or a mathematical convenience? Test 3 is the sensitivity test. We vary the defensible selectors directly to see if the unique point vanishes or shifts. Test 4 is the design test. It checks whether a proposed new observation actually responds to the unresolved direction, or if it is just a redundant data point. Applying these 4 tests provides a systematic filter, separating the artificial precision of the selector from the specific information actually identified by the data. The practical application of this framework is a reporting instrument called the Selector Ledger. This is a machine-readable JSON schema that forces analysts to document their geometry before publication, recording the forward map, the equivalence class, and the selector. The ledger's function is to draw a hard semantic boundary between identified content and narrowing assumptions. The goal is not to prohibit the use of priors, regularization, or calibration in science. These tools are often scientifically warranted and mathematically necessary to produce a usable result. The objective is to stop their contribution from being silently attributed to the data. If the ledger reveals a wide, non-identified set instead of a unique point, how do we use that research to make decisions? It is a mistake to assume that non-identification makes data useless. As this graph shows, point identification is not always required for a robust decision. If the entire identified boundary region safely clears a policy threshold, the decision remains valid even without a single unique answer. By mapping the equivalence class and using the ledger, researchers can provide a more accurate account of what their evidence truly supports, separating the mechanics of the algorithm from the reality of the observations.